Alrighty, same deal as before. I've started us off a little bit further than where we left off before. We had done a little bit of question 7, up until like the second page of it. There wasn't too much more going on there. It'd be easier if we just moved on to the next question to start fresh from there, rather than retread old ground. Yeah, as before, you've got the document and solutions in the chat. This one's actually a better version of the solutions. I went through and cleaned them up. And yeah, we'll start from question 8. Find the coordinates of Q, where Q is the minimum of this graph. Tech-free, by the way. Coordinates of a minimum. In this case, we can quite clearly see the minimum is a stationary point. So using some methods around, or that we're aware of around stationary points will be ideal here. Stationary points, of course, having gradient 0, which means basically having derivative b0. So as long as you're familiar with how to do the derivative of our function, then yeah, what we're going to do is set derivative equal to 0, solve for x, and then, well, yeah, we'll have one of the coordinates. You'll have the x coordinate specifically.
One and negative e to the power negative one.
Yeah, it cut out a little bit as you were saying it, but it sounded like they were good. Let's see. Pull them up. Yeah, e negative 1, negative e to negative 1. Yeah, cool. Yeah, not much different to what I was saying, basically. F of x is a product of functions, so you got to use your product rule. X times natural log x. So you do your u, v, u dash, v dash, plug them into the product rule itself. That gets you your f dash. And then from there, you're just solving a logarithm equaling 0. There's really not too much else to be talked about there. That gets you your x value. Shove back into the original function to get the y value. Sweet. 8b. Using a diff to then solve a related anti-diff. Very common question. We've seen it a few times. There's a few key steps we always want to take under these scenarios. You've got to understand the relationship between the derivative and the antiderivative, how those two interact with each other. The key thing here being to realize that when you anti-derive a derivative function, you get back to whatever the original was. So if you wanted to find the antidiff of x natural log x, there's a challenge there in the sense that there is no immediate thing you can look at on your formula sheet to antidiff that. But what you could do is look at this equation here and antidiff both sides of that, because an antidiff symbol and a diff symbol cancel out. And just like how you can do add, subtract, multiply, divide to both sides of an equation, you can also do diff and antidiff to both sides of an equation. That'll at least start you out. Antidiffing both sides of this equation. That'll cancel out this diff and give you a statement that is significantly closer to getting the x natural log x on its own. So basically that's what I've been describing so far. You're at this stage of the equation, you're basically trying to rewrite this thing highlighted in blue to look as close to x natural log x as possible. It has to look exactly like x natural log x. So basically, you've got to remove that factor of 2, so you only have the integral of x natural log x on one side of the equation, and then all these other terms, so the plus integral of x, the x squared natural log x, they have to be on their own side, as simplified as possible. We still making solid progress on this, or shall I show the answers out? Okay. So, as I said, our goal is to try and get x natural log x, or at least the integral of it, on one side of the equation. One of the things we can do to get closer is we look at this blue highlighted term and realize, oh yeah, if I just take the 2 out of the integral, then I have my integral of x natural log x, like what I want to have happen. So all I've got to do is subtract the integral of x from both sides and then divide by this 2, and then all of a sudden I have that integral on its own. Nice and easy. Because this statement here says the antidiff of this is that. Right? When you have this symbol here, you're saying the antidiff, the integral of that thing, is equal to whatever's on the other side. All we're doing from here is just simplifying the left-hand side a little bit. So integral of x, that's just a basic antidiff of x, half x squared. And then, yeah, just make it look more like the show that. In this case, it's x squared natural log x on 2. So instead of having the half out here, we bring it through and then, once again, have it over rather than just sort of hanging out in the back. And this one's minus x squared on 4. So instead of, again, we've already brought this one through, but instead of having it just sort of chilling at the front, I would then go out of my way to write it on the bottom instead. Even though these are technically the exact same thing, you're better off just writing exactly the way they've written it. Yeah, very common question. It's you got to identify when you have the derivative and the relationship between the derivative and the original function. If you have some sort of like diff equals this, now do antidiff. That's the sequence that's very common, that shows up a lot. Every single time you start by taking a look at the diff equation and then doing the integral, the antidiff of both sides, and then just a bit of rearranging and simplifying from there. Any questions about that? If not, feel free to move on to part C. Keep in mind that x equals a actually is defined on this. It's not just a random point. X equals a is the x coordinate, the stationary point that we found earlier. So if you've already got a copy, you should all have a copy, or at least can see a copy of the exam plus solutions in there. If someone still doesn't have a copy of that, let me know. It'll be good for you to be able to scroll back for these sorts of things. Yep, I can drop another one in. So area bounded by a region, specifically bound by F, the line x equals a, and the horizontal axis from A to B. We're told B is the x-intercept of F, so those things all put together mean we're basically solving that area in there. You've got the line x equals a, you've got b, the cutoff point, and the function. So those are all the lines that make up the perimeter of the shape we're trying to find the area of. And so, yeah, we're now trying to find the bound area, right? Area bounded by all those things. So that's a key specific phrasing around that. Area bound is not necessarily just solving a definite integral. You will need to do the definite integral, absolutely, but definite integral doesn't do area bounded. It does area under a curve, and those are looked at differently. one can be either positive or negative, the other can only be positive. I'll leave that up to you guys to figure out which is which. One problem you might run into is that you're once again basically being asked to do the integral of x natural log x, right? It's the function f, and f is x natural log x. We've actually solved that issue before. Yes, we don't know how to do the antidiff or the definite integral afterwards with a formula sheet. Doesn't exist on there. But we did do something in the previous question that'll make it a lot easier to do that. So some key takeaways so far. We found earlier that the value of a was 1 over e, or e to the minus 1, however you want to do
Oh,
it.
Chris,
Oh, yeah.
is the answer 1 on 4 minus 3 on 4e squared?
1 on 4 minus 3 on 4e squared. Yeah. Oh, right. Yeah, it's right there. That is correct. Yeah, that is correct. There's nothing else to be done there. I just sort of put them in their own thing for no real reason. In my mind, I had this thought that they had a specific form they wanted it. They didn't want it in any form. That was fine. Yeah. How did you do it?
I mean, you integrate it from e to the negative 1 to 1.
Hmm.
And then since like by looking at the graph, you can see that's going to be a negative area. Just put a negative outside the integral just to make sure you get a positive.
Hmm. Yep. Good stuff. And then this integration here, we knew it from earlier, right? We were told flat out, hey, integral of this is that. So there's your capital F of x. Um, Keeping track of the individual terms might have been a bit of a pain. Using different types of brackets, even though it's not technically like correct. Like, oh, this is a square bracket. We use that under different conditions. Like, you're just using it just to make sure you're able to segment your working out a bit easier. Because when the lines get this big, they kind of get a bit confronting. Sure, it's nice for me to be able to color code things, but you don't really have that luxury in the real exam. So I've also provided what I would more or less do with the bracketing around things as well. Yeah, just to quickly highlight where that x equals 1 came from, we were told that the endpoint b is an x-intercept. So you just say, okay, well, x natural log x equals 0. This is actually a null factor law. You've got x times natural log x, two things that multiply together to give 0. So either x equals 0 or the natural log x equals 0. That's where you get this technically invalid, in fact, yeah, why? Where you get this technically invalid x-intercept from. Now, that's simply going to come from the fact that when you sub in x equals 0 into the natural log, you get undefined. Um, but yeah, just thought it was worth highlighting that is actually technically a null factor law situation. You don't just like divide by x, for instance. Yeah, that's C. Sorry, D. I read that and thought it was the question. So G is equal to f of x plus k. So basically the function from before plus a k. K can be any real number. Find the only value of k for which the graph of y equals 2x is tangent to G. So G is this transform version of f. You have this fixed function y equals 2x that's just there on the graph. And you want to play with the k value or otherwise solve for it such that whatever the graph of G ends up looking like is 2x becomes tangent off of it, basically. You have your fixed straight line and you're shifting your graph of G to accommodate that graph y equals 2x. This will test a bit of transformations knowledge. That's only part of the issue though. Doing a little bit of transformations, a little bit of tangent line stuff. I don't think it should be all that bad. Yeah, the main things that come up with tangent lines and transformations more or less are the right way of going about this.
Could K be negative e to the negative one or like negative one on e?
Negative 1 on E. Negative 1 on E is a bit off. Um, so I think the first thing to highlight would basically be uh, this is more or less what you would end up with where you'd want to shift your f of x. Because you've got the graph of y equals 2x, f is currently already here. Having a negative k value would have put this thing down further rather than up. The only way for the new function g in this green MS Paint, the only way for that to be tangent off of y equals 2x is if you shift it up, not down. I wonder what you did to go. What was the main thing you did to get there? Potentially shifting the turning point in a certain way. That's what we had our one on E type stuff before. Oh, you're disconnected. Anyway, point being, you want to shift upwards in this circumstance. I think you might have had an idea around putting a turning point at a certain spot so that it would become tangent off of that. In this case, it doesn't quite become tangential off of the turning point. So looking at towards that is a bit of a red herring. What you want instead to do at this stage, once you understand that K is some sort of vertical translation, is say, okay, well, there's two things that make a tangent line. One is that they intersect at a single point, and the other is that they share the same gradient at that point. So that gives you two things that you have to simultaneously solve for to solve for K in this case. Those are the main things there. I'll just reiterate that one more time because he's rejoined. two main things you have to make happen here. Functions have to intersect each other. So you want to figure out where does the y equals 2x equal g of x. And the other thing you also have to guarantee there is that the gradients are the same there. It's not quite just a matter of what I think was what you were trying to do before, which was shift a stationary point up to a certain spot. It's not quite off of the stationary point in this case. See how we go. So the first thing I did in this circumstance was say, okay, well, where do these things touch? They got to touch at some point. Well, make g equal to y, where y is 2x. And then, yeah, just rearrange for k. Warning, there's a bit of a typo there. That should say x natural log x. So the brackets maintained, but somehow the ln disappeared off of that. So maybe look to the line above for a bit more clearer info there. That gets you k in terms of x, right? Which is cool. We've got something for k that can force k to always force us to pick a value of k that will intersect for any value of x. But we don't want it to just intersect. We want the gradients to be the same at that point as well. So now we just got to figure out how to make gradients the same on the functions. Making gradients the same is just going to be a matter of derivatives being the same. So you find the derivative of g, you find the derivative of y, right? Make those two derivatives equal to each other. Again, y is 2x, so derivative of that is just 2. Derivative of g, we've done that before. G was just f plus k, so we just take the derivative of f that we had from before. I think we did a derivative of f. Yeah, so f dash was just 1 plus natural log x. And, well, plus k doesn't actually do anything. We have this plus k value, it's a constant, derivative of constant always just disappears anyway. So it's still just going to be 1 plus natural log x. And then, well, yeah, you're just going to solve that and then realize pretty quickly that at x equals e, the gradients will be the same on these graphs. Because you've got to realize that plus k just shifts up and down. it'll have nothing. Any horizontal or vertical translation will do nothing to the overall gradient of the graph. So only dilation factors or reflections could do stuff like that. So once we identify where they are going to be the same gradient, what x value in particular, we can just come back to our expression for k, and then we'll just say, cool, x equals e under that circumstance. And so yeah, apparently I had re-derived the entire thing again. You could have just come back here into where the k equals 2x minus x natural log x and just shove e in both of those spots. It's going to get you k equals 2e minus e, k equals e. So if you shift up by, sorry, something just dropped there. If you shift you shift the graph up by e, then you'll achieve exactly what you're targeting there. Yeah, in summary, we had some sort of vertical translation. We had to map to y equals 2x. All we got to do from there is realize, cool, tangents have to intersect at a point, and they have to have the same gradient at that point. Intersecting just means functions equal each other. Gradient means derivatives equal to each other. That's really the main things there. Any questions about that? Let me know. Otherwise, double I. Find all the values of k for which the graphs of g and its inverse do not intersect. Part of that is going to be figuring out what is the inverse of g. Shouldn't be too bad. Inverse of g, you've got natural log. Inversing a natural log should be a fairly natural thing to do, since flipping between exponentials and logs is pretty common in that area of study. You also don't necessarily need it. Like if you can go back to the original graph and just understand, hey, the inverse of this graph is just going to be the reflection in the line y equals x. And so you could just sort of draw it out and then have a think about what would happen as one gets shifted up or down, the other gets shifted up or down along with it in a certain way. No, excuse me, it'd be left or right, wouldn't it? One goes up. There'll be a bit of playing around to consider there. That's basically this, which is if you were to sort of roughly ballpark what the inverse would look like, you might draw something like this and then say, yep, cool. Again, they're only going to ever intersect along the line y equals x. Very common thing with inverses. We want to figure out what values of k would cause them not to intersect at all. Now this is the k equals 0 version, because that's the easiest one to draw. You just stick with the regular natural log, or the x natural log x. which now that I'm saying that out loud, inversing x natural log x probably would have been a pain to do. I forgot it wasn't just natural log. So you kind of do have to rely on these sorts of methods. And then, yeah, if you just imagine, hey, if this thing shifted down, this one will go up a bit. If this one shifted up, this one will go down a bit. Oh, wait, there might be something to do with that.
Would the inverse of g of x also not have a k value?
Also, not have a k value.
Like, wouldn't it have a k value as well if we did the inverse of g of x?
Yeah, but are you talking about like this particular picture that I got up here, or just
Yeah, so now you see the green graph, right?
yeah,
And then that's the inverse, and then the black graph is the normal g, right?
yeah?
I mean that if k was to change in any way, they would both like continue to move.
Well, yeah, that's the idea, right? Which is you want to figure out what value of k will move them in such a way where they don't touch anymore. The picture you're seeing here is the k equals 0 outcome, where there's no vertical translation applied at all, and you just have the original graph and then the inverse of that as depicted. And so you got to imagine, okay, well, starting with the original graph, if I start moving this down, this one's just going to go up. And if I start moving this up, this one's going to go down. One of those is desirable for our circumstance, for not intersecting here. Which way would you want to push it? I guess, thinking about the original, which way do you reckon you'd want to push it?
Probably up.
Yeah, up. Because at a certain point when you shift it up, you're going to get basically this, which is you got your black line, again, shifted now up above the line y equals x, and then eventually, because you're flipping in this line, the green is now, there'll be some point of no return where they don't touch anymore. And so basically, it's a very similar question to what we've just done in the previous question, because you want to find this point and then go further than that, ever so slightly further. This should, like if you ignore the green entirely at this point, just thinking about that top picture, we've done a very similar thing. Like a Sissel test understanding of the previous question, because the scenario is very similar. As soon as g is tangent to the red line, this time it's y equals x instead of y equals 2x, you have only one intercept, and as soon as you're slightly above that, you have no intersections. So if you figure out where there's one intercept and then just say k is everything bigger than that, well, then we're sorted. Let's see if we can implement the previous solution again.
Do we have to push it up more than one on E?
One on E was the hang on, which one was one on E again? We had K equals E last time for the previous one. Um, was one on E from the
Actually, no,
turning
hold
point?
on. I don't think it'll be one on E. Um, do you think it might be two on E? Like it has to be more than two on E?
Why two on E?
My thinking is that okay, so the x coordinate of the turning point is one on E, right?
Yeah, okay, so you're still thinking turning point. Yeah. So I'll point out the other time we did this, we didn't actually get turning point. We had it slightly to the right of the turning point. So um, basically, the key things you have to do here are going to be functions equal each other, and then once you figure out where the functions equal each other, the k value for that, you can then get derivatives equaling each other. Basically, instead of putting a 2 here, you're now going to put a 1 there because we had gradient 2x before. Now we have y equals 1x in this case. Um, because just based on, I know this is my drawing of it, but even if you just imagine like this one over here, drawing a straight line, I mean, because it's sort of concave in a way, the only way you're ever tangent to a stationary point is if you're fully flat, horizontal. Um, so that should be, at least just sort of having spoken it out loud, that should now be a bit of a red flag for any future questions, which is, oh wait, shit, being tangent to a stationary point would actually mean perfectly flat. We explore a little bit of this in Newton's method, actually. And so yeah, just going to be a bit of a repetition on this. In this case, I've done it in the opposite order because it doesn't really matter which way you do this, whether you figure out the x value for the right gradient and then figure out the corresponding k that comes with it, or vice versa. It really doesn't matter which way you go. It's probably slightly more efficient to do the derivative thing first. So once again, you get your derivative of g, which is exactly as before. Make it 1 instead of 2 because the gradient's changed. That gets you x equals 1, where the gradients will be identical. Then from there, functions equal each other. Now, this one is, you can rely on the fact that they intersect on the line y equals x to say, oh yeah, if x equals 1, then y equals 1. So I have f of 1 equals 1, and then I'm just bringing my k back in because, well, we're looking for the k value. Now I've realized I've just highlighted k equals 1 here. I should have said k greater than 1. I just kind of left it as k equals 1. Great. Yay me. Um, so a couple of things there. I need to still tidy up, clearly. But yeah, just imagine this is k greater than 1, because again, we're just trying to shift that black line slightly above, or I guess as above as we can, all of the values above it. Is it fair enough, Neil? It's kind of a similar kind of question that comes up a decent amount. They like to do this sort of inverse pair stuff and number of solutions between them. A lot of the time it comes around playing off the fact that you have to be tangent off of the line y equals x, or at least slightly off tangent of the lines. Cool. Okay, I believe that's the last one. Yeah, looks like it. Sweet. All right, that's exam 1 then. I'll pull up exam 2. If there were any questions about that, feel free to let me know while I pull this next one up. I'm going to quickly print off as a PDF what I had for the exam 2 solutions. They are unfinished, and I haven't looked at them for over a year and a half when I first made them. So bear with me while I'm still tidying these things up. I didn't expect us to go nearly this far into exam revision. Got this one and this one. All right, that should be up. Yeah, those are both downloaded. Okay, question 1. Prove that A equals a quarter. We've got some sort of quartic. You can kind of tell because it's got two power 2 terms in there that are multiplied. Going to give you a net power of 4. So using our understanding of polynomials a little bit, proving A equals a quarter should be a fairly chill introduction into it.
Okay, so if you did f of 0 equal to 4, would that work?
Looks like it. If you sub in 0 and then 4.
No, like, is that like a valid way to like show that?
Oh, yeah, yeah. The only thing I was checking was that you don't cancel out the A. Because I think, if you put -2 or +2 in there, you do actually end up cancelling out the A. So 0, 4 is the only point you could actually use there. Yeah. So if we have a look again, where is it? So much blank space. Yeah, just subbing in f of 0 equals 4. Nice and easy. This one's also probably pretty easy. Part B, especially considering you've got a CAS. This is tech active now. This is a one-liner in the CAS. Yeah, I know the TI Inspire at the very least has an expand function in the algebra setting. I'm just going to double check that the Casio has a similar thing. I'd be shocked if it didn't. Yeah, it's under transformation. Expand. The key, of course, there would be noticing, hey, I've got a factorized form. Here's the polynomial form, the expanded version.
Is B2 and C4?
B2 and C4.
Oh, sorry, -2. Hold up, my bad.
Yeah, B is -2, C is 4. I do want to highlight it didn't ask to solve for B and C, it did ask to give the function. So just keeping that one in mind for when you do it in the real thing. You do need to give the new function rather than B and C in that case. But yeah, you solved it right. Apparently I was insane, and so I also expanded it out manually because, yeah, as if you're going to do that in 2 lines. But yeah, that's all that is. Let's see. This is the derivative of f. Write the rule for the derivative. So there's a hard way and an easy way to do this. Remember you have a CAS. Oddly enough, you'd probably do this faster by hand than by CAS, but only if you use a very specific way of doing it. Really, it's doing that thing again where if I pull up the answers, it covers it. I've been checking it. Okay, whatever.
Chris, do you have to give it in factorized or expanded form?
It shouldn't matter. Factorize or expand should be fine, whichever one you want to do.
Cool. Yeah, I got that.
Yeah, easiest by far would just be to look at this answer you had from before and be like, oh yeah, power down the front, reduce it by one. This is like you'd spend more time in the CAS putting this in for diff than if you had just done it by hand. Now, obviously, if you then if you looked at this one instead and try to diff that, that's a product rule and a painful one at that. So you probably don't want to do that one by hand. But yeah, minimum value of f dash on the interval 0 to 2. So yes, we're doing minimum value, not of f, but f dash. That'll definitely catch out some people in the real deal. Good news is we have a graph here that we can actually just have a look at and be like, oh yeah, minimum value from 0 to 2, it's that thing right there, which I'm assuming you guys can see my cursor. So that'll inform how you go about that. 2 marks, so show some working. No, still did it. I had a feeling the glitch where because I have the answers up on a side thing, and sometimes when I pull them up, it does cover the full screen share. Sometimes it doesn't. I thought it was because of whatever thing was open most recently would get priority. Because I wasn't doing it throughout the class until now, when I started opening up new docs. At least I don't think it was. I was checking. Yeah, anyway. So, minimum value of the graph of f dash, we can quite clearly see that's just going to be whatever that turning point is there. So whatever methods we understand for finding turning points would be applicable there. Just keep in mind you want to apply them to f dash, not f. So it might feel a bit weird, but the double derivative will show up, not because we're doing double derivative things, but because we're simply trying to find the derivative of the derivative to find stationary points on it.
Is it negative 16 root 3 on 9?
Possibly. Yeah, there you go. Negative 16 root 309. Yeah, so derivative equals 0 is always the way to go. Just don't get caught out by the fact that you already have the derivative. You want to find the derivative of the function you're trying to find a stationary point of. You get your plus minus off of that. You'll obviously knock out the negative because you have a different interval. You have 0 to 2. And then, yeah, plug in the one that's according for that. Now, you could just use the fmin function as well. You could do fmin from 0 to 2 as an applied domain to it. That'll give you the x value without the plus minus stuff, so you have to think even less for it. And if you're Casio, it even gives you the minimum as well. So that will be strictly faster on the Casio and slightly faster, maybe, on the TI Inspire. Cool. Part D, bit of transformation stuff. We've got H, which is the same graph but shifted up. Yeah, the same graph but shifted up by 2 and reflected. Yeah, it was a quarter. Now it's a negative quarter. We got F and H that are there on the same axes. We've got to figure out how we're getting from F to H sequence of transformations. And as I'm looking at that question now, I've said way too much about it already. So the only thing left is what order are you doing those things in?
Chris, reflect in the horizontal axis and then shift down to in the negative vertical
Yeah,
direction.
so you're taking F, you're shift down
Oh,
because you're doing it on
we're
F.
graphing F onto H
Yeah,
on.
F onto H.
Okay,
Yeah,
so still reflect
yeah,
in the horizontal, but this time we want to shift it up 2 units
yeah,
in positive vertical direction.
yeah, precisely. You take F, you flip it so it's pointing downwards, and then obviously now you got to shift the stationary points to be aligned with each other. Um, Probably shouldn't have said as much as I did, but I'm hoping it wasn't a particularly hard question to begin with. Yeah, reflecting the x-axis, translate 2 units up, making sure you do it in that exact order, because if you do it otherwise, if you were to shift up first and then flip, you're going to have a very different circumstance, because the axis that you're reflecting in is the x-axis. Now, I have seen I think we have also seen a bit of weirdness around the fact that you can reflect in axes that aren't the x and y axis. You can say like reflect in the line y equals 2. We've seen that before. I forget where specifically, but that was a bit of a weird one. And that was VCAA too, because we haven't done anything else other than VCAA. So one way of doing this, presumably, if I'm remembering correctly, could have been shift up by 2 and then flip in the line y equals 2. That would also achieve it. But that's just me being cheeky. How much of this we got left? Not much. Yeah, we'll be able to do at least E. But I think it might be more important to just sort of talk broadly about what's going on here. So you can see some shaded stuff. It's pretty obvious we're now going to work our way towards shaded area stuff. First one's pretty simple. Where does where does F and H intersect? Well, you just make F equal H in the CAS, and that'll give you all these all the X coordinates for which they intersect. Next up, write down a definite integral that will give the total area. So total area doesn't really matter, it's above the x-axis anyway. And the area is bound by 2 or more curves. In this case, it's just F and G. So we're just doing top take bottom scenarios. The good news with polynomials is that you can do, because they're quite symmetrical in nature, you could figure out the integral of one of them and then just double it rather than do both. That's why it says write down a definite integral, not the definite integral. There's a couple of ways you could go about this. So in this case, it doesn't really matter which one you look at, whether it's this one or that one or both. H is still going to be above F in both of those circumstances. So you're going to do the integral of H minus F, top take bottom, over whatever those X values were. So let's see, how much of this did I write up? Those X values were those, H minus F, or just double one of those. Then finding the actual area, like whatever, in the CAS, nothing to be said there. And finally, vertical distance, find all the values of x for which d is at most 2 units. D is the vertical distance between f and h. So you basically look at your function and think, okay, that's a d, that's a d, the vertical distance between the two. Where is it? Find all the x values for which d is at most 2 units, so 2 or less. So basically, you're looking at the like little bits on the outside here, because at a certain point it'll be more than 2 separated from each other. The way I've done that is actually rather sophisticated. You just do the distance between them, h minus f, because you're doing y value subtracted. You take the absolute value of that, because sometimes this could be a negative, sometimes it could be a positive. ABS should be a function on both CASs. And you just say, hey, where's that less than or equal to 2? Yeah, speed run. If you want me to clarify any of that, feel free to stick around. I just wanted to make sure I got as much in there before people had to leave. If there's nothing to clarify, feel free to feel free to have a good day.